Okay, let's look at some problems that will help us start to review for our Semester 2 exam, our final exam. So the first thing we did this semester was talk about rational expressions and rational equations. So this first kind of section says we're going to perform the operations below and simplify your answers. So we're either going to multiply, divide, add, subtract, or just simply simplify. So in this first problem, we don't really have any adding, subtracting, or anything to do, but I would like to simplify it. Now the key thing is, in all these problems, I want to factor first. So I want to factor the numerator and denominator. So if I'm factoring the numerator, I'm thinking, okay, it's x and x because it's 1, x squared on the front. So I'm thinking of two numbers that multiply to positive 1, which is this last number, but add to 2, which is this middle number. So that would obviously be plus 1 plus 1. So the numerator of factors is x plus 1, x plus 1. Now as for the denominator, it is x squared minus 1. This is a difference of squares. We have x and x, 1 and 1. So if you remember how that factors, x and x, and then it's going to be plus 1 and minus 1. The key thing is, though, you always want to make sure you factor first. You want to make sure you factor tops and bottoms before you try to start crossing things out. Now obviously I see an x plus 1 that cancels here, because it's common in the top and bottom. So our simplified rational expression would simply be x plus 1 over x minus 1. That would be it. Now our second one we have here is a multiplication problem where we have these two rational expressions that are multiplied. Now there's no factoring to do because you notice that there are no pluses or minuses, so these are just monomials. Now the key thing for multiplying is we can still cancel out after it's factored if it was factorable. We can cancel out up and down or diagonally. So for example, I have a 2 and a 14 that I can cross out there, and I'm left with a 7 on the bottom. Similarly with 3 and 9, if I reduce 3 into 9, I get a 3 on the bottom. Now let's see what else we can do. Anything on the top and bottom can cancel. So let's see. I have an x here and 5x to the 5th up here, so I can cross this out and leave me with x to the 4th. Similarly, I have a y here on the bottom, so I can cross that one out on this one with the two y's up here and leave me with y squared. Now if I look at it, so I've got this, let's see what I have left. I have y squared on top, I have this y cubed here, which I haven't touched, and I still have x cubed on the bottom. So I can now see, well look, I have x3 and x4, so I can cross these out, and it'll just leave me with 1x on the top. Now these y's here, they will not cancel out or reduce because they're both on the top. They have to be on the top and bottom to simplify. So those would simply just stay as they are. So our final answer would be y to the 5th, because we have 2 and 3. A single x, so after we canceled all the x's, we only have 1 x left. And on the bottom, we do have something left. We have the 3 times 7, which is the 21. So again, the big idea with multiplication, factor if necessary. This one we didn't have to. Then cancel up and down or diagonally. All right, let's look at number 3. Number 3 is a division problem. 3x plus 9 over 2x squared plus 3x plus 1 divided by x squared minus 9 over 4x plus 2. Now the key thing for the division is we're going to basically turn it to a multiplication problem. And we will do that by taking the first expression. I'm not going to change it much yet. I'm just going to copy it over. And we're going to change the division into multiplication by the reciprocal. So this will be times 4x plus 2 on the top. And on the bottom I'll have the x squared minus 9. So now I'm simply going to try to factor all these tops and all these bottoms and then see what I can cross out. So the first one is 3x plus 9. Now, the one thing I notice is they both have a factor of 3, so I can factor a 3 out. So I have 3 with an x plus 3 left over. Top right is 4x plus 2. Again, very similarly, I can take a 2x out, or 2 out of that, and leave left with 2x plus 1. The bottom right is x squared minus 9, so similar from above, this is difference of squares. X and x, 3 and 3. So this is x minus 3 and x plus 3. I kind of left the 2x squared plus 3x plus 1 to the end because this is kind of the hardest one. So the way we factored that earlier in this year, we use kind of the box factoring. So we'll just kind of write this here and kind of see how we could factor it. So if you recall, we would typically write a rectangle for this. We would put the 2x squared here and the 1 here. And then we would multiply the 2 and the 1, which gives us 2, and find two numbers that multiply to 2 but add to 3, which would be 2 and 1. And then I would put 2x here and 1x here. And then I would just take common factors out of all the rows and columns. So I could take an x out of this row. I can't take anything out of the second row, so that's 1. Out of the first column, I could take out a 2x, and I can't take anything out of the second column. So basically my factors are 2x plus 1 and x plus 1. So if you forget the factor, you might revert back to our notes on Chapter 3 when we learned a lot of those factoring techniques. But anywho, this is going to turn into 2x plus 1 and x plus 1. So now I can cross out these x plus 3's. I can cancel out these 2x plus 1's. So on the top, I'm left with 3 times 2, which is 6. And on the bottom, I'm left with x plus 1 and x minus 3. Okay, so that's a little bit about multiplying, dividing, simplifying. So the next couple deal with adding and subtracting. And the key thing, if you recall, in adding and subtracting these things is to get the same bottoms. So if I look at the bottoms right now, they're x and 5. So the LCD would quite simply be 5x. So my goal would be to write both of these rational expressions with the new denominator of 5x. So to do that for the first one, I need to put a 5 on the bottom, so I'd also put a 5 on the top. And for the second one, I need an x on the bottom, so I put an x on the top. So if I do 5 times 3, that gives me 15. X times x gives me x squared. So now that you have the same bottoms, this is actually really simple. I'll just say the bottom is 5x, and the top is going to be 15 plus x squared. Nothing I can do to factor 15 plus x squared, because 15 is not a perfect square, and it's an addition, so that can't be difference of squares either. Okay, number 5 is a very similar problem. The LCD is actually probably even simpler here because these really have nothing in common. So our LCD is simply going to be both of these binomial factors, which would be x plus 5 and x minus 2. So again, just like the previous one, I want to write both of these with the bottom of x plus 5 and x minus 2. So the first one has an x plus 5, but what it doesn't have an x minus 2. So what I'll simply do is I'll multiply the top by x minus 2. The second one, very similarly, has a bottom of x minus 2, but it does not have this x plus 5. So I'll put the x plus 5 on the top. So now the goal would just be to distribute those numbers. So I'll distribute the 4 here, which gives me 4x minus 8. And here we have something interesting. We can actually distribute the whole -3 and get rid of the whole subtraction problem at once. So I distribute the -3, I'll get -3x minus 15. And this is, of course, all over our common denominator of x plus 5, x minus 2. So if I simplify this, 4x minus 3x is 1x. -8 minus 15 is -23. All over x plus 5, x minus 2. And since nothing really simplifies in the numerator, doesn't factor or anything, this is just simply my answer. Okay, this next problem says solve the equation below, which is a rational equation. It has a denominator and a numerator. So the first thing I'm going to do with these is I'm going to find what is the LCD of all the terms. So the first thing I want to do is I want to factor any denominators. So if you look at the first denominator, it's x squared plus 2x. I can factor an x term out. So that will leave me with x and x plus 2. Plus x minus 1 over x. So now if I'm looking for the LCD of x and x plus 2 and x is simply going to be x and x plus 2. So the way we tried to solve these rational equations is what we're going to try to do is we're going to try to multiply all the tops by this LCD. So I'm going to try to multiply each one, just the tops, by x and x plus 2. Because that's what we said our LCD is. Now the reason we do this, as you will see, is in this case the x's will cancel out. In this one the x's and the x plus 2's will cancel out. So what we're left with is x times x plus 2 times 1, but we really don't need that, equals everything canceled out, so just 1 plus x minus 1 and x plus 2. So what we'll have to do is we'll have to simplify these. We'll have to multiply them and try to get them to be an equation we can solve. So if I distribute the x here, I get x squared plus 2x. On the other side, I have the 1 plus this guy, which I can FOIL. So I get x squared, I get 2x, I get negative 1x, and I get negative 2. So if I simplify everything that's on the left side, I'm getting x squared plus 2x equals x squared. Then I have 2x minus 1x, was plus 1x. And then I have 1 minus 2, which is negative 1. So you'll notice about my resultant equation, they both have an x squared on each side, so I can get rid of that. So really what I'm left with is I'm simply left with the equation 2x plus x, equals minus 1. So if I subtract x from both sides, I get 1x equals 1, which is my solution. So the key thing in any kind of rational equation is make sure you get your LCD, multiply it by each of the tops, cancel what you can. Okay, number 7 is our last kind of review problem from Module 5. It says, what are the vertical and horizontal asymptotes of the rational function f of x equal 2x minus 1? So any kind of graphing problem on a final exam, you can of course graph on the Desmos calculator pretty easily. But in this case, if I wanted to find them algebraically, the vertical asymptotes, which is the first part of the problem, the vertical asymptotes are always whatever makes the bottom 0. Okay, so in this case, it's what makes x plus 5 equal 0. So I could simply subtract 5, so I get x equal negative 5. So this graph would have a vertical asymptote at negative 5. Now the horizontal asymptote you must find by long dividing. So the horizontal asymptote and an oblique asymptote are going to be found by doing a long division problem. Now we only have to long divide until we get to a constant. So once we get to a constant, we're done. And in this case, you'll see it's not going to take very long. So if I take my top, my bottom, which is x plus 5, and divide it into my bottom, which is 2x minus 1, remembering how we long divide, we take the first term here and the first term there. So 2x divided by x is going to simply give me 2. So now that I'm at a constant, I'm really done. So my horizontal asymptote is y equals 2. Now I did not graph this one on Desmos, but I can guarantee I know about what it looks like. If I were to draw a graph on Desmos, I know at -5, we could think of an invisible line like this where the graph will break apart. And there's a horizontal asymptote like this where I know the graph will break apart. So my guess is the graph would look something. The graph would look something like this, where it's broken apart at the vertical asymptote, yet kind of approaches that horizontal asymptote. But again, if you have a graph it on Desmos. Alright, so let's look at some problems from Module 6. So we're going to do kind of the first part of Module 6 in this review, and then we'll finish it up in Review 2. So the first problem says we have two functions, f of x and g of x. F of x is equal to x minus 3. G of x is equal to 2x squared minus 4. And we want to find f composed with g and g composed with f. Well, remember when you have these compositions, whatever one comes second is going to get plugged into the first. So if we're doing f composed with g, that means we're going to put g in for f. So where I have g, so g is this function, I'm going to put it in everywhere I see an x for f. So what that's going to give me is it says x, so instead of x I'll put 2x squared minus 4 minus 3. So -4 minus 3 is -7, because I can put the -4 and -3 together. So that one's actually very easy. You just put one into the other. Now if I want to do g composed with f of x, same idea. But instead I'm going to put f into g. So everywhere I see an x in g, I'm going to put f. So it's going to be 2 parentheses x minus 3 squared minus 4. So where that x was next to the square, I now have x minus 3. So what I would do to simplify this is I would just write the x minus 3 squared out. So x minus 3 minus 4. So that's 2. And this would be x squared, because I'm foiling, x squared minus 3x minus another 3x plus 9 minus 4. So if I put those two terms inside together, I get 2 parentheses x squared minus 6x plus 9 minus 4. So now I'm going to simply distribute the 2 inside those parentheses. So if I do that, 2 times x squared is going to be 2x squared. 2 times -6 is -12x. 2 times 9 is 18. Minus 4. But then I can subtract the 18 and 4. So 2x squared minus 12x plus 14. So even though the compositions were of the same two functions, obviously one was a lot easier. One we just had to basically subtract a number. This one we had to FOIL, distribute, and do all this other kind of good stuff. Okay, number 9 says, what is the inverse function of g of x equal 1/3 x minus 2? Now the key for doing any kind of inverse function, if you recall, is we are going to switch x and y and solve for y. So I don't really see a y here, but if you remember, this g of x is really just another representation of y. So this is really y equals 1/3 x minus 2. So if I want to go about finding the inverse, I will just switch the x and y. So I'll make this x equal to 1/3 y minus 2. And now I'll try to resolve for y. So I'll add 2 to both sides. So that'll give me x plus 2 equals 1/3 y. And now to get rid of the 1/3, I will just multiply both sides by 3, because 3 times 1/3 is just 1. So that'll give me 3x plus 6, because I'm obviously going to distribute the 3, equals y. So now I switched x and y, I have y by itself now, so y is actually g inverse. So the different notation, this g inverse is 3x plus 6. So that is my answer. Now if we wanted to check if that works, give me any point. So let's say I take 3. So I'm going to start with an x of 3. So if I find what is g of 3, so if I plug 3 into my original, I get 1/3 times 3, which is 1, minus 2, which is negative 1. So now if I take that negative 1 and I put it into g inverse of negative 1, plugging that into this function, 3 times negative 1 plus 6 is going to be 3. So you'll see, we start with a 3, we get some number, we put that number in here, and we end up right back at 3. That was kind of the formal definition of an inverse. Alright, so hopefully this was a nice first review to help us start getting ready for our final exam.